This video is about how we obtain information or images with scanning tunneling microscopy. I think it is fair to say that scanning tunneling microscopy is one of the most advanced microscopy techniques with true atomic resolution. That means you even see point defects and differences from atom to atom, which is extremely awesome. Why do I have that in an STM but, for example, not in an AFM? Let's take a look. In an STM, only the closest atom of the tip is interacting with the highest atom of the sample, because the dependence of tunneling current on tip to sample separation is exponential. For AFM, that is a linear dependency, which is why several atoms in the tip interact with the sample simultaneously. You do not get true atomic resolution because you always have interactions with multiple atoms from your sample. Now, similar to SEM or AFM, you have to scan the surface of your sample to obtain information about a larger area. And you can either do that in constant current mode or in constant height mode. In constant current mode, you keep the probe sample distance on a constant level. That means, similar to AFM, you have some kind of a feedback loop that always checks, does the current change? Yes. Okay, wait, I adjust the height. And then sends a signal to the piezo element. In constant height mode, you do not adjust the height of your probe. You keep that at a constant level and measure changes in the tunnel current. This mode is much more sensitive when it comes to atomic resolution. However, there's also a greater chance that probe and sample crash. Before we move on to the spectroscopy mode, let's talk a little bit about the tunneling current first. We already learned that the distance between tip and sample has a significant influence on the tunneling current. Also, if you increase the voltage difference between tip and sample, you will measure a higher tunneling current, basically because you lower the energy barrier. And then the tunneling current depends also on the amount of electrons that are available. If you have a higher electron density, it is more likely that electrons tunnel. Now, is it clear to you what that actually means? That means that you can even visualize subatomic particles. You can visualize electron orbitals as done here in this paper. If you are not familiar with electron orbitals and you are wondering what they are, watch this YouTube video. The link is in the video description. But now back to the spectroscopy mode in an STM. Yes, that is possible as well. For this mode, we do not scan the surface. The probe remains at the same spot and we slowly increase the voltage difference between sample and tip. And as expected, the tunneling current increases with a higher voltage because we lower the energy barrier. However, we also see these little jumps in the curve. And that is where the electron density changes. It is difficult to see it in this figure, but if we take the derivative, we get a nice spectrum that contains information about the chemical identity of the atoms. Now, maybe that was a bit fast and you need a little bit more information as I could provide here in this video. Then check out this website from the Huffman Lab at Harvard University. It contains quite some nice illustrations and explanations about the density of states, which I called the electron density, and maybe that was not 100% accurate and also about the Fermi level, which I didn't mention at all because I wanted to keep it simple. But that's it for this video. Thanks for watching, and I see you in the next one.